We are happy to have at the IFS Seminar today Alessandro Tomasiello. I know Alessandro since more than 10 years. I've been to his lectures in Pisa, where he was doing guest lecturing on supergravity and string theory.
Thank you for the invitation to this seminar series. It is actually a pleasure to participate whenever I can, and I'm very happy that you now invited me to give one of the seminars. Indeed, this topic is one I'm not usually working on. I never worked on. In fact, there are two topics in this title that are not usually mentioned together, and I haven't worked on either of them. So I'm pretty sure I will say many silly things about both, but let's try. So the field of higher spins is, of course, familiar to many people in this seminar, and I'm sure I will be preaching to the choir, so to speak. So forgive me for introducing this, for having this introductory material on the topic, but I wanted to be sure we're all on the same page. So there seems to be a consensus that this is the high spins will play an interesting role in quantum gravity. They have such fields have a heavily constrained dynamics. For example, already at the level of free fields, there are some issues that I will talk about later. But at the interacting level, even more so, so interactions usually, namely from 4 dimensions and up, require an infinite tower of such fields. On the other hand, we now, in spite of these difficulties, we know that such theories do exist. We have, but first, one example is string theory, where high-spin fields do appear, although massive ones. And there is also, of course, the big subject now of Vasiliev-like theories. Another complementary point of view comes from the ADS-CFT correspondence. So this gives, first of all, it gives us an idea, it gives us a reason to believe that the Vasiliev theories are actually really sensible, even quantum mechanically, if one was not convinced already. And moreover, that it is really encouraging because the holographic duals are usually very simple conformal field theories, such as Chern-Simons field coupled to a scalar or to a fermion. These are two well-studied examples. There is also a suggestion, so holography is also this is interesting from my point of view as a string theorist. These Vasiliev-like theories can arise as limits of string theory. There's an example where the so-called ABGM dual, or rather ABJ dual to a solution in string theory, namely ADS4 and CP3, in a certain limit reduces to Vasiliev-like theory, and that string fractionates into Vasiliev. It becomes like a bound state, so to speak, of Vasiliev fields. Moreover, in holography is also shown that higher spins seem to cure the non-causality rather effects that high derivative corrections to general relativity can generate. This is in particular revealed by the analysis in this paper. So anyway, all this is to say that high spins play a really central role in our understanding of quantum gravity. They are not the only ingredient in our understanding, but a very important one. The second topic in the title is perhaps less familiar, I don't know, but I suppose usually it is less familiar to high energy theorists, and it is Finsler geometry. So if you just one possible introduction, one shocking way to get introduced to get an introduction to this topic is this sentence which the late Chern was formed. which says that Finsler geometry is just a Riemannian geometry without a quadratic restriction. What does that mean? So if you look at this paper, it opens with this statement here. You take the line element, and usually, so of course, the line element is some function of the coordinates of your space and also the infinitesimal coordinate displacements. But usually what we do is we take it as a square root of something of this form. And basically in Finsler geometry, we don't do that. Riemann actually introduced had started by considering the whole, the more general story here, but then later he restricted to this case, saying, oh, okay, this is complicated enough. I mean, the most general case doesn't really introduce any aspects, any new aspects, so it's enough to consider this one. Later, Finsler, the first person to go back and look at the more general case, and basically Riemann's assessment was correct, but there are quite a few changes that have to be made to usual Riemann geometry, but as we will see, most of the concepts are similar, at least, to the ones in usual Riemannian geometry. So let's write it a little different, in a different way. So the distance, usually it is written like this, but usually this, like I just said, f is the square root of such a function of the position and of the velocities x dot. And this one, okay, I will often summarize this with this 2G2. G2 because it's quadratic in velocities, and 2, well, for later convenience. Finsler generalization says that, well, this can be any function, not just a quadratic function, but it should be homogeneous of degree 1. Sorry, here it was a square root of a quadratic function. More generally, we'll take it to be a function that is homogeneous of degree 1. Why do you need this? Because otherwise this doesn't make sense. Namely, it depends on what your choice of tau is. The parameter is gamma, and we don't want that. I already said there is the generalizations of the usual ideas of connection, curvature, which I will introduce in due course. And also here I gave the Riemannian case, but there is also the pseudo Riemannian case, namely the analog of Lorentzian geometry. In case you're wondering, wait, what is what are we really introducing that is more more general than what we wrote here? Well, on top of this, for example, we can. This is just an example for now. I'm writing parameterized, but as I wrote it here, it's not quite a complete parameterization. But anyway, just to give you an idea, you can have an expansion where you introduce say, a quartic function, this phi4, according to this general definition, is a quartic function of the velocities, and another one that is sexic, and so on. But this wouldn't be, so since this is f squared, it should be homogeneous degree 2, and if you just wrote G2 plus phi4 plus phi6, it wouldn't be homogeneous. So what you can do is to divide it in this way by G2, the object that you already had, and you will obtain another object that is indeed homogeneous of the correct degree. Now it is no longer a polynomial, it is a more complicated function, but it is allowed by the rules of the game. There are other parameterizations, but I will show you why I prefer this one. To make it, I just mentioned that it is not really complete. It was just to give an example, but well, if you put also here objects like phi3, phi5, and so on, this will be complete. But we'll get back to this later. Motivation for my talk comes from the fact that, well, with this parameterization, I have introduced objects with that are symmetric with more than two indices, like this phi mu1, mu(s). So for example, here that we have a fourth, what looks like an object with four indices, and it looks like a higher spin field. Why not? So if G is usually interpreted as a spin 2 field, perhaps these guys need to be interpreted as higher spin fields. This is an old idea that has surfaced in various papers over the years. These are two examples. Well, here, however, Finsler is not really mentioned, although this expansion is because this is considered as an action for a particle. This is closer to what I will show you today. And then there is also a paper by Hall that has directly made the point that perhaps Finsler should be thought of as a high spin theory. But today, I'll show you what I can do better than those references, in my opinion. This is the plan. First, a lightning review of higher spins, which will be boring to many of you, but to introduce some notation. Then I'll expand on this mini introduction to Finsler geometry, tell you more technically what one needs to modify with respect to the Riemannian geometry case. And then I'll compare the two points of view in the sense that I'll show you that well, basically I'll have a neat statement, namely that the analog of Ricci curvature for Finsler geometry can be written as the Fronsdal equation in a certain sense at the linearized level in this phi that I have introduced in the previous slide. And then, moreover, there is so this is only true at the linearized level, but just like in general relativity, you can expand in your field higher order, and then you presumably can interpret those as interaction terms. So far, so good. These are the encouraging results, but then we'll see that there are also some challenges. So let me not indulge too much on the negative side, because we'll get to it later. First, let's consider the Fronsdal equation. So I need some notation. So first of all, like many people do in the high spin community, I'm introducing a formal variable named y, which so for now, don't think that this has necessarily anything to do with the y's that I have introduced earlier. Sorry, with the velocity, but later with the velocities that I have introduced in the when talking about Finsler. But later I will actually identify the two. So for now, this is just a trick to to condense high spin fields. So this is similar to what we had earlier, this G2. You see now it's the same expression, but with y instead of the velocity. Basically, y will be called the velocity. But the role with the high spins is similar to the one, this formalism is similar to the one that we introduce normally for antisymmetric fields, where we have the x mu with the exterior product, with the wedge product. Now we just have a totally symmetric product of these symbols. We'll often need to introduce derivatives with respect to y, which are like pulling out an index, and this is what they are. So whenever you see a phi with one or two indices, it doesn't necessarily mean that it's a spin 1 or spin 2 field, but rather the spin is this S, and so these are the explicit indices, and then there are some hidden ones. Sorry about this mistake that I keep doing with my keyboard. If I write in this formalism just a product of two such monomials in the y's, this of course corresponds to the symmetrized product of two of these high spin fields. Another object that I need to introduce is the trace, as everyone does. It is very common in the high spin community. From what I've seen, to denote it with a prime. I will also do so. And using it, you can also introduce decomposition in irreducible representations, considering the traceless part and so on. I will also introduce the symbol T for the trace. T, it's just for trace. Sometimes we will need it because I want to have an operator that takes the trace of a field. So these are all algebraic operations. I also need symmetrized derivative, which in this language just looks like this. You have y mu, nabla mu, and the level of the component fields. It is just nabla mu on the phi, but with all the indices symmetrized. And finally, there is also this guy, the dagger, which is just the same notation that you would have for the antisymmetric fields, and it has also basically the same definition as well. So in order to get to the Fronsdal operator, we can just look at what happens for the spin 2, where we can, a common procedure is just to take the Einstein equations and expand them around a solution. And what we'll find is this operator. This basically, well, with a couple of steps, you can also write it in as what people call the Lichner-Hurwitz operator, but right now we can leave it like this. So this H prime is just a trace, so I can rewrite this more symbolically, this equation more symbolically in terms of our condensed notation, like this. In this case, I haven't saved much space, but now an idea that you could have is that in order to describe high spin fields, you could just take the same operator and let it act on symmetric, on a monomial that has degree higher than 2. We call this operator the Fronsdal operator, and we introduce just simply this generalization where the Fronsdal of phi s is 0, and this is just the equation of a massless free high spin field. Of course, this is not, this analogy is not enough to justify this operator. There's more sophisticated analysis behind it, but coming from originally from massive fields and taking the limit where the mass goes to 0, but given that everyone here is an expert, I don't think we need more introduction. So perhaps one more thing I do need to say. So again, everyone remembers this, but the claim to fame of this Fronsdal operator, in fact, is that it basically inherits the same property that it had for spin 2, namely that there is a gauge transformation behind it. Namely, if I consider this transformation, which remember is symmetrized nabla, transform the Fronsdal operator of phi, where now I have taken off all the spin labels to avoid to have more elegant formulae. Well, what happens is that there are some cancellations and you get something nice looking. And not just, the point is not just that it looks nice, but now you can, if you consider the lambda such that the trace is 0, then you find that it's that this f, the Fronsdal operator, has not changed. So this can be considered as a gauge invariance. This has been, this condition here has been regarded with suspicion by many people who suspect that it needs to be improved upon. So there are several proposals for getting rid of it. Actually, we'll see that in this context, and in the context that we'll see today, it is not that unnatural. Another point, I will actually not need this. Usually, if one wants to introduce an action, so it turns out that it is gauge invariant if high spin field has double trace equal to 0. This has been regarded also with suspicion. Around the general curved space, the operator is still the same. So here I was looking at the flat space case, but in the previous slide we had the more general case. And you can repeat the computation. There is a complicated looking formula, well, not that complicated, but the point is that this cancellation doesn't happen anymore, except with some modification when there is maximal symmetry, when this curved space is maximally symmetric. In that case, you do have some gauge invariance again. And this observation can be regarded as the starting point for the Vasiliev theories. Okay, I have bored you enough with stuff that you already know. So I think we can go now to my review of Finsler geometry. As I anticipated, I will also have a y coordinate here. So in the introduction, I was talking about the velocity. But in order to develop this Finsler geometry, it is better to work with more geometrical ideas. And this velocity is usually regarded as a coordinate on the fiber of the tangent bundle. As such, it is better to give it a different name, and people usually pick y. It's a coincidence that both the y has been used both by the high-spin communities and the Finsler community for this letter, and I will indeed identify them. Let's see what changes with respect to the Riemannian case. First of all, so our central object is this F square that I had in the introduction, the thing that you integrate in order to define the distance. If you take the Hessian, the second derivatives, the matrix of second derivatives, you call this a fundamental tensor. Now, it does become the metric, so as suggested by the notation, in the ordinary case where F square is simply a quadratic monomial. But in general, in Finsler geometry, this G mu is not really the metric. We call it fundamental tensor because, in particular, it may depend on these velocity variables as well. It's not just point dependent, but also velocity dependent. So there is as I also mentioned in the introduction, there is a Riemannian case where this distance, this is considered as a distance. Fundamental tensor is required to be positive definite. This is part of the definition of what the Finsler geometry is. But fewer mathematicians have also studied the analog of the pseudo-Riemannian case that is relevant to us. And in that case, this fundamental tensor is required to have signature minus plus plus plus. So now this is, of course, no longer the analog of the distance, but it is to be regarded as an analog of the proper time. Even more physically, the idea is that it could be regarded as the action for a particle, for a free particle in this geometry, moving in this geometry. Mathematicians have considered several examples. They're quite different actually from the expansion that I will consider today, but they have their own reasons. But one example that has been considered, perhaps the most popular example that has been considered, is this guy, where on top of the usual term that we know and love, there is also what we might call a spin 1 field. Notice that this sum is now for F, not for F square. So it's a little different from what we'll have today. And then typically they stop. They don't have this infinite sum that I was suggesting. Also, there are other cases. So this one, by the way, this is interesting because it would be the action of a charged particle. So they considered, what mathematicians have done is considering this as an algorithm of distance. But I will not do that, but it's just to give you an idea what mathematicians usually, what alternative things mathematicians usually consider.
Sorry, can I ask one thing?
Absolutely.
So what do you say that this phi1 contribution is associated to a vector? So usually, like spin 1 comes as a mu x dot mu, so it still depends on velocities, right?
Yeah. So that's what I meant. So I have this notation where phi s is phi mu 1 mu s,
Okay.
y mu 1 y. So this phi 1. Thank you for this question. So phi 1 would be phi mu. Sorry, I haven't written it on the slide. Phi mu x dot mu.
Okay, okay,
So
see.
it is in fact what you had in mind.
Oh,
It's
okay.
just that I have a condensed notation, but it is not. Yeah, so there's this notation where now this is not a one form, but instead of the dx, you have this y.
Yeah, I see. So, okay, I have another related question. So
Yeah.
you keep repeating that there is a relation between length and the action, right? For a point particle.
Yeah, well, yeah. So you wrote to me that this
No,
this
I'm
is not
just
this is
curious
not
about.
innocuous as an assumption. We can discuss this, but yeah, I'll let you finish your question. Sorry.
Yeah, my question is that normally the action is gauge invariant up to boundary terms, even in the case of a coupling to spin one field, while the length normally it should not depend on boundary terms. So I would not say that's exactly the same. Maybe there is some kind of improvement, the next step that one can make.
Yeah. So I can tell you this. So maybe it would be better to take this up after we have seen a little more. But indeed, this is not. It is not clear that this should have anything akin to a gauge invariance. Although I just said that it is something like a charge. So I invited this question because I said that it looks like a charge particle. Mathematicians don't care. They don't consider it as a the action of a charge particle. They just consider it for its own sake. However, there is a notion of something called projective equivalence, where they consider whether two choices of f have the same geodesics. So the gauge invariance that you would imagine for this spin one field does become related to that projective equivalence, even though they don't say it for some reason, but that's how. So there is some manifestation at least of the gauge invariance. But you're hitting the nail on the head, of course, because this will become one of the central themes later on. But if you agree, we can perhaps get
Yeah,
back.
okay,
Because I know that you have followed this, but maybe otherwise the rest of the audience might get a little lost.
Oh, okay, thank you.
Thank you. I mentioned geodesics, but of course I rushed a little ahead because I haven't introduced any geometry yet, really. So, but then of course, it's I think it's natural that for everyone that in order to introduce what a geodesic is, one tries to just to extremize this notion of either distance or proper time, whatever it is. So what you get is, unsurprisingly, I think, so if you do the computation, you find that nothing changes really. Even though this G, as I stressed, is y-dependent, the equation really is the same. The same steps continue to hold. And actually, let me give a name to this G, to this combination that appears in the geodesic equation. People call it the spray coefficient, and they denote it with this letter. We don't usually do this in Riemannian geometry because there's no need for it, but now we'll see that here it's a good idea. So, okay, why are we not satisfied with this expression here? Well, the thing is this. So if you change coordinate transformations, if you change coordinates, if you change the axis, the y's, you have to remember what the y's are. They were the velocity, so the components of the velocity vector. So they do transform in this fashion. So now you have that on the tangent space, you have the combined. I haven't written what the transformation for the x's is, but it's just, okay, x goes into x prime, which depends on x. And the y's will transform like so. So it's a complicated transformation law for on T, on the tangent space, on the tangent bundle. If you look at it from this point of view, the derivatives with respect to the x and with respect to the y's have to transform with the Jacobian matrix, the total Jacobian matrix of this coordinate change. And if you follow this train of thought, you will see that there will be a term here from this doubled Jacobian matrix that mixes the derivative with respect to the x's with the derivative with respect to the y's, which doesn't look that good, which looks a little complicated. So mathematicians have found a workaround to a more covariant object, which is this delta mu. So this transforms well in that this term here goes away, and these deltas transform among themselves like the usual derivatives that we are used to. But we need for that these coefficients n, which are derivatives of the g's that I introduced previously. Remember again that everything here has an implicit dependence on y, so that's really the main complication. Just to give you some intuition, this delta would be reduces to the nabla in the ordinary case. Now, so the reason I spent so much time with this is that everything else you find, so a lot can be done just with this delta. Everything else you find, this is one of the main novelties. And for example, the connection that people use in this context, I mean, there are several, but one of perhaps the most popular is called the chain connection. And it has the same expression as the usual Ricci-Vita, but now with this delta. The thing is that if you look at the concept, the usual properties, but on the tangent space, there's no connection that has all the usual properties. But this one has almost all the usual properties, only it doesn't respect the metric if you consider the derivatives with to y. But those perhaps we care a little less about. So this capital gamma is really what gives the most elegant geometrical properties. Okay, so now we can get to the curvature since we now have the connection. And so believe me, this is of course I'm cutting a lot of details, but so there are many things that you could introduce, and many of them are introduced by considering derivatives with the y's. This will be important later. I think this might be part of the origin of my issues, let's say. But
Alessandro, there is a typo in that equation. Maybe gamma upper index should be mu, I guess.
You are right. Gamma upper index is a mu, yes. Let's see if that fixes it. Yes, thank you. Well spotted. This one is correct. Okay, thank you. In fact, I lied. There's another typo, not a typo, an intentional typo. This is actually defined usually without this G, and it's an object with 3 indices, and again with this being a mu. And then I've taken that this would be called the mean Landsberg, really. And there's also this mean Cartan. Anyway, I simplified things, and in my rush to simplify, I oversimplified. The most useful guide to us, however, is the analog of the Riemann tensor, and maybe unsurprisingly to you now, you have to use the gamma that I introduced earlier, capital gamma, and this delta. So this capital gamma, remember, contains this delta. It turns out that it's much easier to compute this object directly because it has a compact expression in terms of the G that we introduced earlier, and this helped me quite a bit. But remember that this, in spite of this guy having 2 indices, it really has in its belly all of the information of the Riemann. On the other hand, if you consider the trace of this guy, rho mu mu, it does contain the Ricci now, because it will contract these 2 indices. Basically, in the ordinary Riemannian case, it would be Ricci YY. This concludes my review of Finsler, and now let's see what we want to do with this. So we now have the Fronsdal equation describing high spins, and we have reviewed Finsler geometry. And now we have the 2 are nicely alliterating for some reason. And not because of this, I'll try to put the 2 together. I will, of course, not describe you things historically, let's say, but I'll pretend to be very wise, and I'll do the following. So first, I'll study what happens. So I'll tell you what happens if you if you deform this f squared by delta f squared. So you change this all-important square function of the x and y by something else. And this is similar to what you do when you perturb g mu plus h. Okay, so you have for the spin 2 actually, we did this in the introduction, in the first part of the talk, and we had some formula, and a similar formula can be computed for this rho that I just told you about in the previous slide. I'm making things a little easier than they are because I'm okay, here there will be a second line that I'm just writing as terms with Landsberg and Cartan, which are these objects defined in terms of y derivatives, where Carapet found the typo in the previous slide. But look at the rest here. Maybe this is evocative. So if you deform, if you take, so this is general, and I have, so if you look in the paper, you can see what the other terms are. But if your original f square was of ordinary type, namely just a quadratic function like this, it turns out, well, so these are the Landsberg-Cartan of the original thing that you are deforming. And if you remember, they were defined in terms of y derivatives of the metric. But the y derivative of the metric is 0 for the ordinary case. So these go to 0. And moreover, so the delta, I told you already that it reduces to the nabla. And sorry, here I have introduced this d without really telling you what it is, but it's an analog of the delta when you are acting on things that have indices on top of having explicit indices on top of having the y indices that are hidden in my notation. But both become just a nabla in this case. So then this d, this delta become nablas, and you stare at this operator and you recognize that, well, this becomes just a Fronsdal operator. This is because basically this is the trace, because it has a double derivative with g mu, and that's just the trace operators we saw a few slides ago. This is the thing that we are, so this is this rho for the thing that we are deforming, the original f square. And so at the linear level, I can write this, that the rho is the ordinary one plus this object, and this object turns out to be just the Fronsdal operator on the nose. So the slogan here is that the Ricci analog, the Finsler analog of the Ricci tensor, if you want Finsler Ricci, is the Fronsdal operator of this delta f square. That's really the reason that these two appear to be related. We can make this, perhaps it looks a little too symbolic. So let's try to make it more concrete by using the expansion that they introduced in the introduction. So perhaps I can justify that. I can justify it a little better. So the idea is that f squared is a function of the x and y's. But okay, so let's pick x to be a point, and then it will be a function of the y's. But the y's, so as a function of the y's, it is actually homogeneous. Degree 1. So we don't really care about the dependence on the radial coordinate in this y's. We really care about the angular coordinates in the y's. So we can think of it as a function on the sphere in the y coordinates, or well, in the pseudo Riemannian case, perhaps the hyperboloid in the y coordinates. But if you think about the sphere case for a second, we need, so we cannot use the Taylor expansion in the y's because this is a homogeneous function.
Alessandro, I have a question. May I ask a question?
Yeah.
Concerning this expansion, in terms of phi 3, phi 4, do you assume your fields to be traceless or not?
No, exactly. I was getting there. Indeed, well, you see that what traces.
Otherwise, this expansion is just ambiguous.
I will explain in a second. So first, very good. So so if you look for, I was saying, you cannot use the Taylor expansion. So what else do you have? Well, on a sphere, you would have the basis of spherical harmonics. But what are spherical harmonics? So an efficient way of writing spherical harmonics is in terms of the coordinates in the ambient space, so which would be the y's, but homogenized. And so if you follow this logic, you will get here, basically. You will get an expansion like this. Strictly speaking here, I could also introduce, so I started with this spin 3 field, spin 4 and so on, but I could have a spin 1 and spin 0. So I haven't put them here explicitly because I'm interested in high spin fields, but a complete expansion would also have those. So, but let me write this expression here. Now there's the thing that you're asking about. So in the spherical harmonics, for the spherical harmonics basis, these phi's should be traceless also. Otherwise, this expansion is redundant. For example, the spin 1 and spin 0 can be generated by having, I don't know, the non-traceless part in phi 3 and the non-traceless part in phi 4. But more generally, so if these are not taken to be traceless, what happens? So what is the redundance? The redundance is generated basically by this that I'm calling the trivial gauge invariance here. If you transform, I don't know, phi 6 with this delta k, so if you say that you activate the non-traceless part in phi 6 by this kappa 4, say, you say delta kappa of phi is minus G2 kappa 4, and simultaneously you also transform phi 4. Well, you have done nothing because the two terms compensate. The G2 inside phi 6 will cancel with the change you have done to phi 4. I hope perhaps I haven't explained it in the best of ways, but the idea is that in order for the expansion to be complete, first of all, you should also have the spin 0 and spin 1 parts here, but then phi 3, phi 4, and so on should be irreducible, hence traceless. On the other hand, no harm is done. So perhaps we can also keep this redundancy by not putting them to be traceless just for a second, because we will keep it as a redundancy because it's some sort of gauge invariance that I have used as a cross check on my computation. So we have this trivial gauge invariance that can be useful sometimes. With this expansion, with this spin expansion, so you can plug it in this result that we had before, that the linearized part beyond the 0 order looks like this. And you plug the sum in, basically. And what you get is that you have now more explicitly this Fronsdal operator, the individual phi s, plus this term. Why? Well, basically because the double derivative that we have, so so when I said that we got the Fronsdal, but a little bit in a formal sense. The trace operator was really the second derivative of the y's. But when you act on this object, you have that it generates the trace indeed of the individual fields, but also derivatives of this G2. And when all is said and done, you have generated this additional term. So as I was saying before, I have used so if you don't take the phi, you can take the phi's to be reducible, but if you don't take them to be reducible, you can check that this trivial gauge invariance respects this expression. So, and this in fact is another way of fixing this coefficient. So it's a cross check on the computations that sometimes can be useful. So I should say that this this paper here had the spin 4 example of this statement. And what I've done is that I found that it extends to all the spins, and that unfortunately there is this correction term. We'll see why, unfortunately, in a second. Beyond, so this was the linear, all I told you so far is about in this section about the Fronsdal versus Finsler is at the linearized level. but what happens beyond the linearized level? Well, in principle, in the paper, you can find the full answer, but let me give you here just a taste of what happens by considering what the answer if we set all the phi's to 0 except for phi 4 and phi 6. The spin 4 part of rho, full linear level is full nonlinear level, that remains just the same as before. But for so you're basically expanding also rho in spins with the same expansion we saw for F squared. And for the 6 spin part of this rho, of this Ricci, you get, well, this was the linear part that would have been predicted by the formula in the previous slide, but then there is an extra quadratic object that contains phi 4 and its derivatives. So it is natural to think that this is, okay, so this then grows in complexity in higher spins, but you can ask me about it if you want. But it is natural to think that this is some kind of interaction between 2 spin 4s and 1 spin 6. Why? Because it's a bit like what happens in general relativity, where when you expand in H, you will find that the equations of motion, that you have the linear equation in H, which you use for gravitational, to find the free term for the graviton, but then going to higher levels in H will give you the graviton interaction. And this is a similar idea. So if you're really optimistic, the picture, if you were optimistic, the picture that you would end up with at this point would be that that this is the coupling, gets interpreted as a coupling to a particle, and that perhaps this Ricci Finsler that or Finsler Ricci that we saw can be considered as the analog of the so like an equation of motion for some higher spin fields with some interacting structure that is completely fixed by these geometrical principles, just like in general relativity. This will be the hope. Having stated the hope, I will now at least partially destroy it. So far, so good with the good news. Now we'll give you the bad news. A nagging thought that you might have had from the beginning is, well, so Finsler geometry is invariant under diffeomorphisms. It was built to be invariant under diffeomorphisms, just like ordinary geometry. But in high spins, for high spins, we would also like to have these invariances that we had for the Fronsdal operator. Do we have them? Well, let's go back to the linear case. This was the formula that emerged. So we had an expansion in spins for this Ricci, Fronsdal Ricci, and they contain the Finsler Ricci, sorry, and they contain this Fronsdal operator plus this with some coefficients. So now the transformation of this is d3 of lambda prime, as we saw. But there's also this, and this also transforms. And since phi is transforms as d of something, the whole thing becomes d cubed of some object. You might say, oh, very good, I have a good coincidence here. It looks like some kind of Stueckelberg formalism, because I can use the highest spin transformation parameter to eat the lower spin one. So for example, the trace of lambda 5 it will be related to lambda 3 and so on. And so every spin transformation would be eaten by a higher spin, one with an even higher spin. This might look promising. However, this, when you consider this more carefully, this is exactly the trivial gauge transformation that we had seen earlier. And this doesn't do anything to the geometry. This is the reason I have called it trivial. So in fact, this eating results in no real gauge transformation being left. I regard this as a problem. I think what it means is that there are no higher gauge transformation in spite of appearances. So at first it looks enticing, but as it is now, I think it is not satisfactory. Let me say it in a slightly different way, and then I think I can conclude. Maybe the way I have presented it is a little complicated. So I can also introduce a total capital lambda, which is a sums of the candidate gauge transformations for all the higher spin fields. So from this point of view, if you have this, if you want to avoid the redundancy that that appeared earlier, you can do the same. So just like for the higher spin fields, also for these higher spin transformations, you would take them to be traceless, which, by the way, is this what people don't like about high spin gauge transformations. But here it is kind of natural. The thing is, then the transformation for this linearized raw will be just this simple formula, which again looks promising. However, now you would like, so it is really like what we are used to. You have the trace of this capital lambda now. However, this is a trace. What is this trace? It's a second derivative in the y space. So it means that this capital lambda should be harmonic in y. On the other hand, we know that since f squared needs to be homogeneous degree 2, this capital lambda needs to be homogeneous degree 1. So if you group them together, there is only the only answer is that lambda should be linear in y, and these are diffeomorphisms basically. So we don't. So this might have looked confusing, but we don't have any extra gauge transformations. I have also looked at more exotic ways where you might think, oh, okay, maybe this didn't work. T lambda equals 0 doesn't work, but maybe once you act with the d cubed, things can change. But I think no one will be surprised by hearing that this doesn't work. Do I have time to tell you about one? I think this is the last slide, actually. Besides conclusions, it was argued that I have my equation of motion in my the hope that I was given was that the equation of motion was simply Ricci equals 0, just like in with the gravitational field alone. So there's an argument that this actually doesn't come from an action, and some people have have looked for something that does come from an action. What they do is this: so you have the usual measure in the X space, but then you, and if you like to integrate the Ricci, you divide by f squared in order to make it homogeneous of degree 0, so that you can integrate it also in Y space. But you need to also, if you don't integrate in Y space, you have something that is Y dependent. You need to integrate also in Y space. And that adds another guy like this. So this is the measure on the angular part of the fiber of the tangent space. Okay, looks complicated, but people have done it, and they have they computed what the equation of motion is. Instead of being Ricci, this rho equals 0, it is Ricci equals something else. I mean, these two terms look a bit like the Einstein tensor, but then there are also these Cartan guys that I introduced a while ago. And this might give you some hope. Perhaps this guy does have a gauge transformation, but the analysis is actually pretty similar. The two go hand in hand, and not much changes really. So I claim that also here there is no gauge transformation, and I don't have to tell you that this is bad. So if you look at if you were to have these equations of motion without gauge transformations, then well, you can. I have confirmed that explicitly just to be sure, but you expect that you would have non-transversal modes, modes that are non-transversal to p mu, and those will create trouble when you quantize, as we are familiar from other cases. We saw some promising signs. This was the hope that I showed you at some point. So the part that is most promising is the fact that the linearized level, the Finsler-Ricci tensor, really looks like a Fronsdal operator on these phi's that I have introduced in the Finsler distance. And moreover, at the nonlinear level, you could imagine interpreting the nonlinear level as interacting, as some kind of interaction with between these higher spin fields. However, we saw that in a subtle way, the highest spin, in spite of this, even though the Fronsdal operator appears, and the Fronsdal operator usually does have this gauge transformation, if you do things more explicitly in terms of this expansion that I showed you, on top of the Fronsdal, there is another term that breaks it, breaks this gauge transformation, not quite completely, but breaks them so that they become simply a trivial reparameterization of this. It becomes the trivial redundancy of this parameterization of the Finsler distance that I showed you. The pessimistic view is that this Fronsdal appears only for mathematical reasons. And so maybe it's a bit of a coincidence driven by the fact that after all, I don't know, maybe mathematically things have to work in a similar fashion. After all, I have motivated the Fronsdal operator from the spin 2, and well, maybe there are only so many ways that you can write things. But maybe there's a more optimistic view where what I've done is just maybe just the beginning. So in order to reintroduce the gauge transformations, perhaps you can change them a little bit and not just have d lambda as we usually do and introduce some complexity in terms. Or perhaps you have to change the equations of motion beyond what because I've considered after all just the stupidest object, not stupidest, I mean the most natural object, the Ricci. But as I have tried to show you, there are many notions of curvature that people have introduced, and many more that mathematicians haven't bothered to consider, because after all, you can take many derivatives with y's. So maybe with a little luck, one can change the equations of motion so that the gauge transformations reappear. Bear in mind that we don't need to have the gauge transformations appear on any background, because this also doesn't happen for ordinary high spin fields, where the gauge transformation, remember, as you know very well, only appears, say, in ADS, but not for any background. Thank you.
Thank you, Alessandro. Questions?
I have actually 2 comments, not questions. First of all, it seems that the fields you work with are actually conformal high spin, not ordinary Fronsdal high spins, because your component fields, they are either traceless as conformal high spin fields or traceful. It is not enough to have just a Fronsdal operator. You need special spectrum of fields, and to obtain Fronsdal equations, you need double traceless fields. And I don't see how can you
double
tracelessness condition from this construction, in this construction.
It doesn't emerge, I agree. So the way the story is usually taught, but perhaps you'll tell me that I'm wrong, is that the double tracelessness appears because you want to write a gauge invariant action, but that particular gauge invariant action. But I thought perhaps we can consider other actions, and indeed I showed you one, and maybe the double trace constraint is not that important if you want to try writing other actions. On the other hand, this is wishful thinking, I know. By the way, Dmitry Panomarev wrote to me with identical, well, he didn't, he also felt rather strongly that this is only likely to lead to conformal high spins rather than ordinary.
Yeah, and
it is a natural expectation.
Yeah, and it is related to my second comment, because there was some old paper by such a guy, Arkady Segal,
That's what Dimitri pointed out to me. Yes.
In the phase space, yeah, in the cotangent bundle rather than tangent bundle, and this approach has some advantages because there is a natural way to introduce gauge symmetry just as a canonical transformations and to write down action functional. But again, it is possible only to reproduce conformal high-spin theories, not usual Fronsdal high-spin theories, because of this subtle double tracelessness condition.
Oh, again, because of this. Okay, I see. That's a very concrete possibility that this would can only work there. But in fact, it might, well, not even there, it is guaranteed to work properly.
Maybe I can also comment about this double tracelessness. So again, I think your comment, Alessandro, is correct in the sense that if you are able to write Fronsdal equation, then that's enough, even if field is not double traceless. If you derive from your action the Fronsdal equation itself implies double tracelessness rather subtly. I mean, if you are able to write exactly the Fronsdal equation, then you don't need to assume in advance.
Yeah, if someone hands it to you, exactly. If someone, that's what, yeah.
But the problem there normally is that in order to write an action that gives you Fronsdal equations, you have to assume double tracelessness. But
that's a reason. Indeed, that's a reason I wrote it in many slides ago.
Yeah. Another comment is that actually the higher spin fields with conformal symmetry, as it seems that you have here, because you have the redundancy that is a gauge freedom to shift the trace. So this is an extra gauge symmetry, right?
To shift the trace of each guy independently, right?
Yes. Yeah. That is another symmetry in this.
I mean, in a sense,
right?
you shift one, but at the cost of someone else's. So you can shift the trace of phi 6 by changing phi 4 at the same time.
Yes. So in a sense, the trace part is redundancy, and you can shift it. So in a sense, it is, yeah, you can think of it as having trace shift symmetry, and that is.
And I think this is the reason this is the reason that it appears. So it appears also in the paper by Segal, which I'm sorry I hadn't considered.
Yeah, no. What I wanted to say is that I mean, one can start studying the theories with such symmetries, but not necessarily work with the full conformal higher spin actions. You may have something that is somewhat similar to Fronsdal, but because having this extra symmetry, it might deviate a bit from Fronsdal, but describe the same spectrum. I mean, there was some work by Xavier Pekar, Ehan Chung, and Jihad Murad. I think they were basically doing this induced actions from taking conformal higher spin fields without, like, you can think of it as a background field, couple it to scalar, then integrate out this scalar, and this way you can find full nonlinear actions for conformal higher spins. What they noticed is that, so I don't know how well it is written in the paper, but what they noticed is that you get not only the standard conformal higher spin action, which is a full nonlinear action, everything is fine, except that it since it has higher derivatives, it has Ostrogradski costs in it. But also they found some other actions, including two derivative one, which was rather exotic something because they realized that it doesn't give Fronsdal if you linearize it. But the symmetries seem too much.
Some other action that also has the same property, so the same also describes.
Yeah, it has the same collection of fields, the same symmetries, including shift symmetry, and the linearization that they looked did not give Fronsdal, so they didn't do much about it. But in a sense, again, it gives some nonlinear theory that has similar properties as what you're mentioning. And yeah, maybe final question is that, so I wasn't completely sure that I follow why you say that that means that there is no gauge symmetry. Because if you have some condition that you have to fix each of the trace of the parameter with the other parameter, this is only condition fixing the traces, right? And if you think in terms of Fronsdal fields, normally they have traceless parameters. So if you are able to get rid of these traces, you are still left with a collection of traceless parameters, no?
Let's consider this, right? So
Yeah.
here, if I want to set this to 0, I will have the
Mhm.
lambda prime 5 is lambda 3, and so on.
Yeah.
So this is non-zero. So this doesn't mean that, so far you do have some solutions to this recursive equation.
Yeah.
But I claim resulting lambdas
Mhm.
correspond to this redundancy.
But
That they
this is
are
a
just
bit.
they are a particular case of this. So in particular, if you were to, a particular case where you take kappa is d of something.
No, I want to think of these two as separate, distinct symmetries, because in my understanding, the lambdas are gauge symmetries, and then these kappas are Weyl symmetries. If you are not mixing them, then I don't see why. So you can gauge fix kappas by working with the traces of the gauge field, while you can gauge fix to have gauge invariance for lambdas by fixing the traces of the gauge parameters, which are different things.
But if you say that you trace this by taking them to be, taking the fields to be traceless, and
I'm afraid then you have to try to find some compatible gauge for also lambdas, because in a sense, when you have Fronsdal equations, these are not traceless equations. If you want to gauge fix your fields to be traceless, you probably have to project also your equations to traceless part.
no, so all I'm saying is that from the Finsler point of view, since they are all connected, collected into this object. So if this F square is the only place, if F square is the only place where they, in physics, where the phi's appear, then you lose nothing by doing this.
Well,
Then,
except that this phi's in your action, if you are off-shell gauge fixing them to be traceless, then now you are variating with respect to traceless fields to get your equations, and these equations should be projected to traceless part.
no, I understand, but at this point I haven't. I'm just looking at the equations as if they came from above. I have this rho to 0. Later, I also consider this a more complicated equation, which has more for which I need more details. I mean, this is a simplified discussion where I have only rho equals 0 as an equation. Like I said, I mean, this is unrealistic because the rho equals 0 is not, cannot be derived from an action. I mean, it has been shown that they cannot be derived from an action. So you see, I'm in a way, I'm consistent.
These equations are non-Lagrangian, so there is no problem to assume that this is from the outset.
On the other hand, there is this other more complicated. You see this other guy here. The analysis will be more complicated. I cannot just tell you what I wrote there. I also find that this doesn't have a gauge transformation, but the argument is longer, lengthier, and it is in the paper. But you see, because it has also all this stuff here. You can imagine that it becomes more involved. But if you are happy for a second to forget about this case and go back to the simplified discussion, then so exactly so as was I don't know, maybe Alex said it. So there is no inconsistency because I'm doing something unrealistic anyway. Okay. So
I have one more short question concerning these equations. In principle, it is possible to write down meaningful equations for ordinary high-spin fields in terms of traceless fields, yes? But then you need to impose some constraints on the gauge parameter, differential constraints. For example, there are such what they call Maxwell-like equations of motion for completely traceless fields. Dario Franchi, Skvortsov, Vasiliev, and some other papers.
If we are thinking in terms of traceless fields, then this can be also understood as gauge fixing of Fronsdal. So in a sense,
yeah,
when Alessandro's gauge fixing is phi prime to be 0, is going there, so he has to also gauge fix the gauge transformations with lambda. If he's not imposing lambda trace to be 0, then he has to impose divergence.
Yeah, divergence of the gauge
plus
parameter
gradient of the trace of the parameter should be 0. And then one has to make sure that this new condition with which he is trying to gauge fix is compatible with the other one.
So maybe it is possible to somehow find these more complicated equations.
You mean these ones?
Yeah, to reproduce these Maxwell-like equations in the free limit.
That would be great. I was hoping that something would pop out. I even put some coefficients here, and I repeated the analysis, hoping that something special would appear in the analysis for gauge transformations exactly for these values of the parameters. But I don't know, it doesn't seem to happen. I have to say, I haven't done it really in ADS, which is where the thing should be done. So I have done it to some extent for ADS, and I convinced myself that it wasn't. So my understanding of this case is less clean. I think right now this equation is not the correct one. I'm reasonably sure. But I wouldn't, perhaps there's just a little bit that has to be changed. And maybe, okay, maybe I will look at this Pancha Skvortsov proposal with that.
So like not to afraid to impose some differential constraints on Euro gauge parameters. It is possible to reproduce some high-spin equations in terms of traceless fields and
I have to say that
constraint gauge parameters.
Okay, well, that's a good input because I was a little bit afraid. I mean, this one, for example, I tried to say, perhaps the whole thing needs to be 0 rather than just this to be 0, but this doesn't really lead anywhere.
Yeah, the symmetrized gradient being 0. I mean,
it does exactly. Well, it doesn't.
It mostly means that whatever is under it is 0. Yeah.
It has some occasional. It has some occasional kernel, but basically nothing. So,
yeah. If you have traceless parameter and you also have traceless field, in order for your gauge transformation also to be traceless, you have to have divergentless parameter. So just take trace of the gauge transformation, you will see that. That's
maybe this might be a good idea. Thank you. For completeness, let me mention, so I'm talking to one of the authors of this more complicated equation. After we actually I managed to talk to them only, actually to Pfeiffer, one of these people, only after I had already written a paper, suggested that perhaps, well, first of all, I shouldn't regard this, this I imagined, I shouldn't regard this as a totem. I mean, it's something that cannot be modified. I mean, this was just a proposal. But also perhaps just like, we find the gauge transformations around the ES, and maybe here we might find them around a certain background that is not quite Riemannian. Even though this is Finsler, I'm always perturbing around a Riemannian case or pseudo-Riemannian. But perhaps the background is Finslerian already, the one where the gauge transformations can appear. So in a way, this you might view this kind of Stueckelberg as encouraging. I don't know, but to my mind, it looks a little trivial, and it does nothing to kill the dangerous modes. So what do we want from the gauge transformations? We don't just want them to be there for any reason. I mean, we want them to kill the transversal modes. And I have checked explicitly. Maybe this part in the paper is not very readable. I don't know, but I have checked explicitly that I mean, this trivial thing that remains is not enough to do that.
So in other words, in principle, you might say that there is a parameterization also for gauge parameters, and we can choose them to be traceless. But when we do that, then condition that you had will impose that all the gauge parameters are 0.
Excellent.